I have a great concern about the concept of energy because I think that it's simultaneously the most important concept in all of science and engineering, and at the same time the least well understood. And so in the next few lectures we'll be trying to rectify that. I feel compelled to start with a definition of what I mean by energy. It's one of these things, and many of you have heard me say this before, that a common thing is for a person to use the word energy. We use it all the time. It's a very, very colloquial term. And then if I ask the question, what do you mean by energy? The answer is, energy, as if the word itself somehow contains all the understanding. Well, it only contains the understanding if we agree on what we mean by that. And the answer that I've come up with, you won't read this in any book, is that energy is one of a number of universal symmetries. And what I mean by symmetry, I think I've mentioned before. You think of symmetry, for example, the first thing that pops into mind, I think, is left-right symmetry. A thing looks identically the same on the left as it does on the right. It is symmetric. But that's not the only kind of symmetry. If I have a vase and I turn it through a certain angle and it looks the same from your direction because it has no distinguishing features, like there's no handle on it or whatever to move around, and I turn it around, it is symmetric in rotation. So what symmetry means in physics is sameness. And if you think about it, it's the most critical feature of our universe. If our universe was absolutely anarchy, and there was nothing consistent or nothing sameness about it, there would be no algebraic physical laws, there would be no order, and there would be absolute chaos in the universe. The very fact that we live in a universe of order, that right now the sun is rising, that there is a sun and planets that go around and galaxies and cosmic formation and so forth, and that there are physical laws that govern the whole thing. Laws like gravity and the recently discovered or measured gravitational waves and fancy things like that. The reasons why they exist fundamentally is because there are things that are the same about the universe, consistencies that can be relied upon, that are the hook that create an algebra that allows you to solve for things. So energy is one of a number of symmetries of the universe. That is a number that you can calculate, that remains the same or changes in a predictable way no matter what occurs in the universe. So this symmetry, this sameness that I'm talking about, is the energy. It's not the only symmetry. I said one of a number of symmetries. One of the other symmetries that you might know about is momentum. There is a law of conservation of momentum that we'll discuss at a later time. That's a symmetry. It is an easier symmetry, and I'll explain why. Another symmetry is angular momentum and its conservation. It is an easier symmetry. Another is charge and its conservation. It is an easier symmetry. The reason why is that there's only one kind of momentum. There's only one kind of angular momentum. There's only one kind of electric charge. Whereas there are many different forms of energy. And that can make it challenging for us. I think you all know that there's a kind of energy referred to as the kinetic energy, and that there's a kind of energy referred to as the potential energy, that among the potential energy there are many forms. There is also thermal energy, field energy, all kinds of energies that we create. So it can be quite profuse. And so calculating the number that is the energy can be complicated because I have to consider energy in its many forms. So our discussion today is simply one form of energy. Consider an arbitrary trajectory through space, right? It's a path that an object is following, and here it happens to be. It's an object of mass m that is moving through space under the influence of a force. I'm going to sort of draw the force in an arbitrary direction here. There it is, force F. I just made that up. And I appreciate, according to Newton's second law, how this force will modify the velocity of the object in time. The modification of the velocity, of course, is the acceleration, because F is equal to ma, and that's the way the whole thing works, and the direction of the change of the velocity is exactly in the direction of the force that I've shown in my diagram. And so the reason why the trajectory through space is curved the way that it is, instead of a straight line, according to the inertia of the particle, is the action of the force. You agree with me, because you understand the mathematics of vectors, that are arbitrary of any physical or independent of any physical law, that I can take any force and decompose it into its components in any coordinate system that I choose. That's an arbitrary thing that I can do. So I choose, for my own education here, to derive some components. I'll find an angle, theta, that is the angle between the force vector and a line drawn tangent to the curve here. And I'll find the component of the force that is directed parallel to the trajectory, and I'll call that F parallel, the parallel component of the force. That is the component of the force that is directed along the line tangent. There is also a component of the force that is directed perpendicular to the tangent of the trajectory. And I'll draw that here at this instant shown in the diagram. And it sort of goes off in this direction. And I'll call that F perpendicular, the perpendicular component. I understand the action of these components in time because I understand Newton's laws and I've already applied them to this situation. The component of the force that is parallel to the trajectory will in time increase the magnitude of the velocity. That's its role in Newton's second law. Because it is in the direction of the velocity, because I could have certainly drawn a force where this component would have turned out to be anti-parallel to the velocity, but in this particular case that I've drawn, it's in the direction of the velocity, so it will increase the velocity. That's its role. The parallel component of the force will increase the velocity in time. Give me an instant of time dt, and I'll tell you the modification of the velocity dv based on that component of force. The perpendicular component of the force is slightly more sophisticated. It will not, in the next instant in time, change the speed of the particle. It will not change the magnitude of the velocity in the next instant in time because it is perpendicular to the direction of motion. What it will do, however, is it will create a change in velocity perpendicular to the velocity vector, and that changes the direction of the velocity. You should consider in your mind circular motion, where a force is exerted perpendicular to the velocity as an object goes around in uniform circular motion. That force perpendicular to the velocity does not increase or decrease the speed. It merely changes the direction of the velocity vector. It merely changes the direction of the velocity vector. In time, I am interested in how these forces modify the velocity of the object, in particular the speed, not in time, but in space. That's the argument that I want to make. Because I have an object that's moving along with a velocity v, and I give it a certain amount of time dt, there's a certain change in the velocity associated with that. That is acceleration, I understand, because I've already investigated those laws of motion. So now what I'm going to do is ask, how does this parallel component of the velocity, the perpendicular component, I understand changes the direction of the velocity vector, that's fine. I'm interested in how does this parallel component of velocity, F parallel, how does it change the speed of the object in space? So this is the way that I'll proceed. This parallel component of velocity is equal to the mass times the acceleration. Now the acceleration by definition is the mass times the derivative of the velocity with respect to time. You'll notice that I've dropped the harpoons off of this. This is certainly a vector equation, right? But I've dropped the harpoons because we understand that forces are vectors, and this is a component of a vector force that I've defined in my diagram, and we know that the velocity is a vector. I'm interchanging the word velocity with speed because that's a very casual thing to do. I can do that because the object does not turn around in my argument or discussion, so the magnitude of the velocity is in principle the speed. But I'll have more to say about that in just a moment. So this is how the parallel component of the force changes the velocity in time, because this is Newton's second law, what I've written here. This parallel component of the force here naturally is F times the cosine of theta, as I've drawn it in my diagram, because you see that the parallel component of the force is the adjacent component. So I write that out, is equal to the mass times dv dt. Now I'm going to do quite a curious thing, and you might wonder, why do you even take this step? Well, the steps here are quite absurd. Why would you ever think to do that? But it turns out that you do it, and then later on there's some utility. So I'm doing some centuries-old physics here, and so we already understand the value of it. But the curious thing is that I'm going to multiply both sides of this equation by dx. A curious thing to do. The only thing that makes it not curious, I guess, is that I'm interested in how the velocity or the speed is being changed in space. So I've got to get some space into it. So in order to insert some space into the problem, simply multiply both sides of the equation by dx. Now, the left-hand side is not of so much interest to me today as the right-hand side is. I see what's happening here is m dv dt dx. Now, realizing, of course, in calculus that the dv dt is in fact a fraction, I can manipulate it a little bit by writing it as dv times dx divided by dt. Because all I've done is shifted the dt, so then now it's under the dx instead of under the dv. And so this will be equal to m times dx dt, I recognize, of course, is the velocity. So it'll be mv dv, which is equal to, all the way over here, on the left-hand side, f cosine theta dx. Well, I have both of these sides of the equation expressed as differentials. The instinct to integrate it is just simply unavoidable. And so I'll integrate this side. So the integral of the force times the cosine of theta dx is equal to, on this side, the integral of the mass times the velocity dv. Now the mass does not depend on velocity, I'm claiming today. A curious thing is in tomorrow's lecture, I'm going to claim that it in fact does depend on velocity. But right now, I realize as a practical matter in my physics that when I put a thing on a scale, it has a certain mass. And I put it on the scale, it has a mass. I put it on the scale, it has a mass. And it always has the same mass, because that's the mass. I make measurements of the mass, and so it is. And so it doesn't matter how fast the thing's going, right? So I pull the mass out of the integral, so it's the mass times the integral of v dv. I'll consider the limits here. What is my velocity going to do? Well, let's say I start with some initial velocity. I could start with 0, but I get a less general law when I do that. So I'll start with v0. I'll go from v0 to v. And those will be the limits on my integration. This integral is spectacularly easy to compute, because the integral of v dv, naturally, is v squared over 2 dv. And so this is m times the quantity, v squared, divided by 2, evaluated from v0 to v. Well, I think that some of you certainly have already recognized what this is. It's a very, very familiar quantity. This is 1/2 the mass times the final velocity squared minus 1/2 the mass times the initial velocity squared. So what effect, I'll go back to my original question, what effect does a force applied in the direction of motion have in space, not time? Well, that effect is that it changes this quantity. Do you see that this quantity, this mysterious thing, 1/2 mv squared, is evaluated here at the final velocity and evaluated here at the initial velocity? This is the change in the quantity. This quantity, as I think you're all very, very aware, is known as the kinetic energy, given the symbol capital K. In more advanced physics, it's given the symbol T, and I have a strong temptation to do that, but it is K, the kinetic energy. The kinetic energy is 1/2 the mass times the speed squared. I mentioned already in the discussion that there are profusion of energies, that there's not just one kind of energy. There's kinetic energy and potential energy, and among the potential energies there are many energies. Well, one thing that all energies must have in common is that they must have the same units. And I can observe from this what the units of kinetic energy should be, because I simply look at the equation. The kinetic energy is units of kilograms, meters squared per second squared. A kilogram meter squared per second squared does not roll trippingly off the tongue. A kilogram meters squared per second squared has another name, doesn't it? You all know what it is. It's a joule, of course. Energy measured in joules. Now, Richard Feynman once said, I can't quote it exactly. I should have thought to look it up before I had this conversation. But Richard Feynman said something about, if you want to, this is totally paraphrased, if you want to understand the folly of physics and physicists is the number of different units that we have for energy. Joules is the most common one for our classical mechanics, but there are a zillion different measurements of energy. Someone asked me one time, what's your favorite unit? Not unit of study, but what's your favorite unit of measure? And immediately I have an answer for that. It has to be megajanskis per steradian. That has to be megajanskis per steradian. That's a wonderful, wonderful unit. If you have a radio telescope and you're looking for aliens, the intensity of radio signals that comes to your radio antenna is quite weak, you can imagine. Cosmic signals are not very, very high energy. And the unit that's used to measure that, if you see radio telescope data, like here's what it looks like, look on the y-axis, it's megajanskis per steradian. We'll talk about steradians later. You'll enjoy that a lot, because I'm not sure where steradian comes from. I think it actually means stereo radian. So if you, I'm making that up, but I got to believe that's what it is. Yeah, it's three-dimensional. It's the unit of solid angle, the steradian, stereo radians. What? Blurp. I don't know. STR. Well, we write rad, so I guess just you write ST rad. Yeah, so capital M, I don't know, Jansky, I don't know what that is. I don't know, something like that. Look it up. But for now, we'll content ourselves with the very simple unit of joules. Every energy that we define, every energy, without exception, can be expressed as units of joules. But as I say, there are a zillion units that are equivalent to joules, but just with a conversion factor or whatever, because we do a lot of physics on different scales. A joule is a fantastic amount of energy. So you imagine when I'm doing particle physics, I do not use joules to describe. I use what are known as electron volts. There's a unit of energy on the very, very small scale. And then there's GeV and so forth. You've heard in particle physics experiments. So joules, the unit of energy. So I could say that the kinetic energy is 1/2 the mass times the speed squared. And we commonly say that. It is actually 1/2 the mass times the velocity squared. How do I square a velocity vector? Just a word about it, because it's a little bit strange. I've never actually mentioned how do you square a vector? The square of a velocity vector is actually this when I write v squared, it's actually v dot v. It's the vector product of v with itself, which naturally turns out to be a scalar, which is why v dot v very rarely comes up in our physics as an issue. There are a couple of little fun places in physics where you have to point out that it's actually v dot v, and then you take some advantage of that in derivation. But not here, but I just wanted to mention that it's actually the dot product. So that is the velocity squared, but I'm comfortable in all of our classical mechanics saying that it is in fact the speed squared. So what I realize here is that what I have on my right-hand side of the equation is that the effect, and this is what I was talking about, what I was looking for, the effect of a force in the direction of the motion is it changes the kinetic energy. It changes the kinetic energy. A force impressed upon an object through space changes the kinetic energy. So how do I calculate that effect? Well, I have to go all the way back over to the left-hand side of the equation here and realize that this is how it's computed. What's a curious thing? dx is the displacement in the direction tangent to the curve that I drew here in my original diagram. And I have f times the cosine of theta. So I'm going to replace this expression with something that is much more general, and I'm going to deal with it more in a future lecture. But realize that this is integral of the force in scalar product. So I use a dot with a displacement. This is an integral form. I've used dr because it's not necessarily x-axis, right? I could go y-axis, I could go z-axis, or r could be an arbitrary direction in three-dimensional space. So I've written this thing in the most general way that I possibly can. This is a quantity that many of you are already familiar with. This is called work. Not work in the colloquial sense. I'm working right now, in the sense that I get paid to do what it is that I'm doing. Work in the scientific sense is exactly what I've described here. The action of a force through space to change the kinetic energy of an object. And so if I call the work capital W, which by the way, in a much earlier lecture I would have said that I do not use capital W for the weight of a thing because I have a far, far better use for capital W in my physics. Well, there it is. Then I get as my final result, W is equal to delta K, which of course is known as the work energy theorem that can be applied to all manner of problems. Pointing out a utility here. When I take the force and I calculate the work, I do so with a scalar product, which means work is a scalar. It is not a vector. When I calculate kinetic energy, I calculate it 1/2 m v dot v, which means work is a scalar, not a vector. In this way, energy has a much greater utility for understanding the behavior of physical systems than Newton's law does. Because Newton's law is a vector equation. I need to worry about the components. And as you've done problem solving in your homework, you've realized that vectors are pretty much a major pain in the ass. And forces, sometimes difficult to understand their action, context of a free body diagram. My recommendation to all students of mechanics is that whenever you're solving a physical problem, use energy first before you try using Newton's second law. Because energy is all scalars. And working with scalars is easy. You add, subtract, multiply, divide, knock yourself out. Use energy first before going to Newton's laws in order to solve a problem. There are some cases where Newton's laws will turn out to be the more effective way to go, but far, far fewer. Almost all of our problems from here on out will be solved in the context of energy. And interestingly enough, if you go further with this, you will find that in the branch of physics known as quantum mechanics, near and dear to my heart, there are no forces. There are no forces in quantum mechanics. Quantum mechanics is a theory entirely of energy, because it will turn out that it seems like everything is energy in fields, and there are no forces. But that's a deeper sort of metaphysical idea about what's going on. The work energy theorem can be applied, and every remaining lecture, until we get to our exam on this material, every lecture from here on out is sort of the details of that being applied to physical systems, the work energy theorem, a fundamental law of the universe.